We're going to do a lot of demos today. We're going to work with the ideas that we started last lecture, and we're going to be talking about a new idea for you guys in physics called conservation of momentum. Okay? And in general, conservation laws. So what conservation laws generally imply is that some physical constant remains the same. So in this case, momentum remains constant. That means that momentum is conserved. One of these that you probably all know is the conservation of mass, right? You probably learned this a long time ago in middle school science that mass is essentially conserved, or we at least approximate it to be true for most of our physical models. So today, we're going to explore some of this. So last time we introduced momentum. We're now going to talk about the conservation of momentum, which we've addressed already in some of the homework problems. And we're going to use this to show there's a series of new problem-solving strategies. Okay? We're also going to talk about a different type of momentum called angular momentum, which is also a conservable quantity. Okay? So let's just review really quickly before we start exploding things and doing things that are dangerous. We're going to talk about the conservation of momentum. And last time, recall that the sum of forces on an object was equal to mass times acceleration. This was Newton's second law. And we showed that it's the time derivative of this quantity, mass times velocity. So I can write this mass times velocity as a thing called momentum. So we define momentum as the velocity vector times mass. And the reason Newton did this is that he realized that the change in this quantity, momentum, implied that there was a force on the object. So if you're running straight, imagine you're running on a track, you're running straight, and somebody comes and pushes you from the side. There was a force applied, and your velocity vector suddenly changed. Okay? That's the idea that Newton basically used to understand dynamics. And so the rate of transfer of momentum, dp dt, how fast your mass or velocity changes with time, is what gives you the force. This is just, again, Newton's second law written in terms of this new thing that we called momentum. And if you start from Newton's law, you can go to this thing that we call the impulse momentum theorem. We talked about this last time. So all I do is I take Newton's law, force equals the time derivative of momentum. I integrate both sides, f dt. Remember, the area under the force time curve gives you the change in momentum. So momentum transferred by a force over some short time is basically what we would call impulse. And so we defined it that way. We said, let's define this impulse due to a force, J, as the integral under a force time curve. You remember all of this? Right? Probably complicated last lecture, but now you're all experts in it. Right? Okay. If you're listening, you would laugh at yourself. Okay. But here's the idea. There was now a theorem that tells us how to understand how things will move, right? Mechanics. And the theorem says that if I take the sum of all forces on an object, and I look at the impulse created by those forces, I can figure out how the momentum has changed. Okay? So this was the basic theory, and it really comes from Newton's law. It's basically a time integral of Newton's law. And if you look at the units of this thing, it works out that the momentum is mass times velocity, so kilogram meters per second. Impulse is force times time, but that's equal to kilogram meters per second as well. So the units in this theory work out, and so we're going to kind of explore a bit of this. Okay? Here's the first thing we did last time, and I want to reiterate it to see that it's actually quite simple. Is let's imagine a very simple collision. And I think I can even do this if I'm careful. Let's do it this way. Get rid of these two. And get rid of this one. Okay, so here's this little Newton's cradle. You've seen these before. It's just on the projector screen. We're looking down on it. I can imagine a collision where I move these two spheres away from each other, and then I'm going to let them go, and they're going to collide. Okay? So do you see this motion? They're basically coming in. You can hear them clicking as they hit, and then they're bouncing back away. Now just watch one, and I'll try to pitch them so that they're not bouncing so much. Did you see the collision? Slow motion. Okay? This is what I'm going to draw, and we're going to ask, how does that all work in slow motion, right? So here is the velocity of the sphere on the left moving to the right. Here's the velocity of the sphere on the right moving to the right, this one moving to the left. remember what we said about momentum problems is you have to kind of frame it as here's before and here's after. And then you ask, what was the momentum before and what was the momentum after? So we can think about in that collision, these two things clack together, and there's a third law pair here where the force of 1 on 2 has an equal and opposite force of 2 on 1 for a short amount of time. And you remember we plotted this last time as a function of time. This force basically grows to some maximum value and then shrinks. In the case of these hard spheres, that function is actually very steep because there's no compression, or there's very little compression and very little extension like you would have in a soft object, like that guy's face when it got hit by a soccer ball. But in any case, there's a third law pair. The forces during a collision are an action-reaction pair. So in that instant when they interact, it's a pair, and then we know that they move out with the opposite velocity. Okay? So now with our understanding of momentum, we can see something really important about this, and we'll see it in a lot of demonstrations today. Let's just apply Newton's law on object 1, so mass 1. Okay? So this should be a little familiar to you, right? The force on object 1, in this case, when they collide, is the object's basically number 1, so the force of 2 on 1 is being pushed, and that's going to change its momentum, right? I can write the same thing for object 2. The change in object 2's momentum is equal to the force of 1 on 2. No mysteries, right? It's just application of Newton's second law, but we're just using this new form of change in momentum. But we know something about these forces. What do we know about these two forces? Force of 2 on 1 and force of 1 on 2. They're equal and opposite, right? They're a third law pair. So we know that this one is equal to minus this one in magnitude. And so we can actually use this to think about this problem in a new way, which is taking the sum of all of the changes in momentum. So I'm going to say, okay, I want to take this change in momentum of 1 and this change in momentum of 2, and I'm just going to rewrite it, right? I can say the time rate of change of the sum of these two is basically written just what I've done. I just add them together. I add up all the momentum in the problem all at the same time. And what I can get from this previous statement is that the time rate of change of number 1 is the force of 2 on 1. The time rate of change of number 2 is just the minus of that force. And those forces have to sum to what? If I have two forces and I add them together and they're equal and opposite, I get 0. Okay? So in this problem, right now, when I hold these two spheres, what is the total momentum of the system? Look at the screen there where I'm holding these two spheres. What is the total momentum right now? 0. Did I hear it? 0. Okay? What is it when I let go? There's a total momentum in the problem. There's a negative velocity and a positive velocity. There's two positive masses. What is the total momentum going to be when I let go? Still 0, because they're opposite, right? So when I let this go, this system, even though it's moving, the total momentum in the system is fixed. Do you see that? That for every time that these two are coming together, they're canceling each other's velocity. When they move apart, they're canceling their velocity. So when I add these together, whether in the collision or in movement, the momentum is always 0. Okay? How could I make the momentum change in this problem? How could I make it change? I can add a force. I'm going to hit this one again. I've now changed the momentum in the system. Now it has a different momentum, but it's now fixed. If there's no forces acting on it, the momentum is constant. Okay? So we can see that the two momenta, when I add them together, it's some fixed quantity. That the momentum of this closed little box on the projector screen is fixed. And I can say that the total momentum after the collision is exactly the same as the total momentum before. Right? I had two spheres coming in with opposite velocities. We said the total momentum was 0. After they collided, they both went out at different velocities. The total momentum was still 0. And it's going to be that way unless there's some external force acting on the object. Okay? That's what the theory tells us. You just saw it for a second there. Now we can actually ask more about this. So Newton's cradle can be more complicated. So why does this work? Everybody knows what's going to happen. If I take I take this sphere. Why is that twisted? Hold on one second. Okay. If I take one sphere and I lift it, right now, what is the total momentum on the system? 0, right? There's no velocity, there's a bunch of mass. I'm going to let this go. And what happens? I take momentum from this sphere. There's an impulse on the next sphere. That sphere imparts an impulse on the next one, which imparts an impulse on the next one, which then finally gets to 1 at the end and changes its momentum. Now think about this from another point of view. Look at this one here, the one at the end. Okay? What is its momentum right now? Okay, what will its momentum be immediately after it gets impulsed? Right? It's not 0, right? When I think of this system by itself, that's the closed system. If I add momentum to it, there's now momentum in the system. So when we think about this idea that momentum is a conserved quantity, you think of it like money in a bank, right? I added momentum to the system, and it stays in the system, unless I apply another force to take it away. So even though this sphere started off, and I can actually do it the other way so it's moving kind of more intuitively, even though this one started off at 0, when I add momentum by releasing this one, it now adds finite momentum. But the sum of momentums of all are still 0. Okay? So you have to, here's the trick. When we think about momentum, we have to ask, what system are we talking about? If I put the two together like this and I say, what's the total momentum of this system? That's a fixed quantity, it's conserved. If I think about 1, and I ask, what happens when this one collides with it? I can add momentum to that system. I'm exchanging momentum. I take momentum out of 1, and I put it into the other. Now we can push this model a little bit further, and you'll see again familiar topics. We'll come back to these demos in a second. But imagine just in general, right? I can have collisions. Just imagine billiard balls on a table, a flat table, just collide. So the total momentum of any system that I choose, I could choose these 5 Newton's cradle spheres, I could choose 2 billiard balls on a table. Any momentum in that system is just the sum of all of the momentum of its components. Right? So these have mass of A, mass of B, and they have some velocity vectors. Okay? Now, if I look at this system and I say, well, what's the time rate of change? I know that that's related to force from Newton's law. So if I can change the momentum, it's basically the time rate of change of the first one or the second one. Right? If I change their momentum, that means there were forces involved. And those come from all of the forces acting on A, could be anything, and all of the forces acting on B. Again, it could be anything. It could be gravity. It could be a car runs into them. It could be anything. So when we take all of those forces together, I can break this down. I can say, well, there's 2 forces going on here that I know a lot about. There's the force of B on A and the force of A on B. But what are these forces? These are the third law pair. So they cancel to 0. Right? The force of A on B is equal to minus the force of B on A. This piece goes to 0. And then you just have a sum of all other external forces. And this is exactly what Newton told us, that the change in momentum of any system, right? I conceptually draw a box around these 2 objects, and the change in momentum of those 2 objects depends only on what force I add to the system from the outside world. Otherwise, it's fixed. If there's no force acting on it, these things could be bouncing around or moving in any which way, but their total momentum is fixed unless I throw something extra in the system. So the time rate of change of a system's total momentum is equal to the external force, the net external force acting on the system. And that's what Newton's law specifically says. Now, if the net external force acting on the system is 0, right? Let's take again this system. What is the net external force acting on this system right now? Effectively 0. We're ignoring gravity. There's no extra forces bouncing these things around. If that's true, then the system's total momentum is conserved, right? If the sum of all forces is equal to 0 from this equation, the time derivative, the rate of change is 0, and if something's not changing in time, it means it's a constant. So the total momentum in this system is constant. Why does it slow down? If I just said the momentum has to be constant in this system, let's do it again. Why does this thing slow down? Where's the momentum going? Where? People are pointing in different directions. What do you hear? Why do we hear sound? It's basically vibrating. It's vibrating in the air. You hear those compression waves on a little thing called your eardrum. And that's energy leaving this system. Every collision in this system is a real collision. So the total momentum is actually lost in these kind of energetic sound waves being pumped out of the system, and friction and a whole bunch of other things. So this law that we've written, this principle of conservation of momentum, is basically ignoring all of these real features like friction, heat loss, sound. So this is the ideal principle of conservation of momentum. Those things basically are other ways of thinking about external forces. This is creating a force on the outside world, and so it's basically changing its momentum. Okay? Here's a demo. This one's fun. There's not currently an active shooter in the room. Be warned. Okay? So this is a cannon. Let me show you what it looks like. I'll draw a picture on the board. It's a real cannon. Here's a cannon on a little cart. On wheels. Okay? And here is a big block, again on a cart, on wheels, and a big chunk of clay. And they're hooked together. Okay? If I take and load this with a bullet, and I shoot it at that other block, what's going to happen to the system? What? I heard two different things. I heard one person said it's going to shoot this way. I heard another person say it's going to do this. If they're tethered together with a beam, which is it going to be? I heard all different things. What's going to happen? All right, let's do it and then we'll decide. Okay? Okay, if you're not paying attention, you will in a second. Where did it go? Wait. Before you're so excited, where did it go? It didn't move an inch, right? It didn't move even a millimeter. Okay? Why is it true? Why did it move?
It's getting pushed, but there's recoil at the same time, so it cancels out.
Did you hear what he said? This is a good intuition. He said it's being pushed. There's a force. So the force of the bullet going this way, there's an equal and opposite force going the other way, which we call recoil, and they cancel out. Okay? When I lit this thing, were there any forces from the outside world acting on the system? No. So what does that tell us about the momentum of the system? It has to stay zero, right? If it stays zero, this thing doesn't move. Let's try a different one. Here's the question. If I take the little bar away, so I can redraw this. Where can I erase it? Yeah, if I take the bar away, add more firecrackers. I'm kidding. Okay, now here's a question. Now that we have a deeper understanding of this. If I take the bar away, and I now do the same thing. I shoot the cannon at the other block, and that hits that block. What's going to happen in this case? The total momentum before is what? Zero. How can I make these things move in a way to keep the momentum zero? What did you say? That's exactly right. They have to move in equal and opposite directions, or with equal and opposite velocities, right? So when I take two objects, if I'm not putting any external forces on the system, the momentum has to stay fixed. The only way to keep zero momentum is that they move out this way, right? Okay. Let's see if it works. Give me a minute. I have to clean out the old firework. Now, here's one thing to note. These fireworks are probably, again, as old or older than you. So they're baby doves. That first one, I think we were lucky. Okay. Matches. Okay, ready? Again, eyes up. If you're sleeping, I apologize. Looks good. Everybody stand back. Okay. They're not connected now. I've removed the bar. Let's look at the picture. Again, it might be a dud. It's really anticlimactic when it is, but we'll try. What happened? The two cards went in which directions? Straight opposite each other. Why? What was the total external force on the system? 0. Any force of that projectile going this way, there's an equal and opposite force of the projectile on the cannon pushing it the opposite way. That projectile did the same thing on the other one. It impacted that object. There was a force going this way. The object had an equal and opposite force on it. All the forces in this system had third law pairs that canceled to 0. There is no way to introduce in this system an external force that would have given it a net momentum. So we notice that before and after, the momentum is what in this system? It's 0 in this case. Now, if I were to do this experiment with both of them rolling, what would happen? The total system would have a net momentum. Would that momentum be fixed or would it change? I hear some people say it would change. If I just rolled this along a frictionless rail, the momentum is some value. What does the law of conservation of momentum tell us? If there's no external forces acting on it, what will happen to that momentum? It stays fixed. That means that what would happen if they were linked and I moved them together, they would just keep moving in the same direction. They would have the same momentum. If I did that and then they tried to blow apart, the momentum of their center of mass would be the same. Okay? Do you remember moment of inertia? We said, what's the distance from the object to the mass? This is how we calculated the center of mass of objects. When we think about a system like this one, this is a closed system, the momentum of the center of mass, sorry about the fireworks. It's like you guys don't realize we live in LA, the worst air pollution in the entire country. Ranking for one of the worst in the world. This firecracker is not doing anything. When we think about momentum problems, let's go back to this. When we think about them, we think about the total momentum around the center of mass of these objects. In this problem, the total momentum around the center of mass was some point in between the two parts. At the beginning, that was 0. It wasn't moving. When they blew apart, the center of the mass stayed fixed. It was still 0. Okay? So this shows us that at least to 0th order, our ideas are right. Okay? Now, here's another one. This is a cool one too. That's counterintuitive. Anybody familiar with CubeSat? Usually the engineering students like CubeSats a little more than biology. Nobody knows what a CubeSat is? Wow. Okay, here's what a CubeSat is. You can buy one. If you want to start a Kickstarter, you can start a company to buy some CubeSats. Basically what a CubeSat is, it's a satellite that's about this big. I think it's about 18 inches. Okay? It's about this big around. It's actually a square profile. And you can send these up into rockets and do experiments out in space. So if you have a really good idea, we can pool our money, we can build this little satellite, send it out in space. Eventually it comes crashing down to Earth and burns up in the atmosphere. But in the meantime, we get some data and it's a cool thing. Here's what, does anybody know Bill Nye? Yeah. Okay, good. Slide, and we'll talk about this in a second. Let's say that we wanted to build something that was going to accelerate through space and time. Just like Bill Nye. If I had a light sail, that'll come up in a second. There it goes. All the way. There we go. Okay. Imagine I had a light sail. Here's this light sail in profile, and I wanted it to go this way. Which way would I fire particles at it? If I had a particle gun, I would shoot these particles with that velocity, right? Now, when that particle hits the sail, let's say that this particle has a momentum of P1, okay? What happens if that particle sticks to the sail? How much momentum did I just transfer to the sail? P1, okay? Is that me? No. I'll put that down. Okay. Okay, so everybody, I think a lot of you said I would transfer P1 to that solar sail, and it would now have a new momentum. You see how this could work, right? Particles of light have momentum. You can shoot them at things. If they absorb that light, it would push it with some momentum. Now, what would happen if I instead made this out of a mirror, okay? And I shoot this particle of light, and afterward, it's going out with a reflected momentum of P1. How much momentum did I transfer to my solar cell? Say again. I hear P1. Let's look at this problem again. We did this 3 times last time. Let's see if we remember. Here's the momentum before. So before, I have a momentum P1, right? What's the momentum of the sail before? 0. Okay? Let's look at just the momentum of this particle. What's the momentum of that particle after? It's negative P1. Does everybody believe that, right? It's bouncing in the opposite direction, opposite velocity. What is the change in momentum of that particle? What's the change in momentum? 2 P1, right? The magnitude at least is 2 times P1. So if this particle sticks to the sail, how much momentum was transferred to the sail? If it sticks, just P1, because it started with P1 after it was 0. If I bounce, I get 2 times that momentum change. So if I said that what this particle is doing is bouncing and imparting that momentum to my sail, what's better, to bounce or to have the particle absorb? To bounce. That's why that sail, which I showed you, was a mirror and not a piece of black film. Right? If I wanted something to be a good absorber, I would make it black. If I wanted things to bounce, I would make it a reflective mirror. Okay? We can actually see this. This is with light, but you can do this classically. Let me show you this weird thing. There are 2 kinds of... This is a very simple demo. It's actually surprising. There are 2 kinds of plastics, essentially, or rubbers. One of them, watch what happens when I hold this one back. I'm going to hold this piece of wood. Now, watch what happens to this one. What happens if I lift this up? It does what? It bounces, right? Where's the energy going? It's getting lost to all sorts of things. I can hear it a little bit. There's wind resistance. It's not ideal, okay? But now there's this other kind of rubber. It's, I think, neoprene. You can do the same thing, and watch what happens to it. Did you see? What's the difference? This is the first one. Bounce, bounce, bounce. This is the second one. That's not. Otherwise, they feel identical. You can't actually tell the difference between these by squeezing them. You can't tell the difference by their mass. They're, in a sense, identical. Okay? Now, if I do this demo, the idea is this. I'm going to take the one that doesn't bounce. I'm going to hold it to this height. I've just put a little rail here so that I can see how high I hold the other one as well. Now, when I do this, I want to see if I can knock that board over. What am I doing? I'm imparting momentum to this other object. Let me see if it works. No.
So close.
Okay. So close. Right, but not enough. Now, what we just said was that if I have one that bounces, it does what? It imparts twice the momentum. This is the same mass, moving the same velocity by the time it gets down there. Will it knock it over? Fingers crossed. Everybody close your eyes and we'll just go for the risk. Okay. So it's exactly what we just solved, and you solved several times last time. Let me find my pointer. That when an object reflects, its momentum has changed by a factor of 2, right? It was twice. It changed from momentum P1 to 0, and then from 0 to minus P1. When it's absorbed, when the two stick together, there's less momentum exchanged. If I exchange momentum between this ball and this solar sail, you see that I've applied essentially a force on the solar sail. Right? I brought momentum from this system into that system. So the change in momentum is equal to the impulse that solar sail sees. Now what Bill Nye has done with the Astronomical Society is say, let's build a giant solar sail that effectively moves without fuel. All it's doing is reflecting at a very high finesse, they call it, it's reflecting solar photons. Does that make sense? Simple mechanics, yeah. Well, that's why it has to be so big. So basically what they do is they build that solar sail so that there's enough momentum exchange to basically start to move it. Now here's the thing, this is a good question actually. Let's say I put this sail out in space, it's kind of floating there, and I start imparting a fixed amount of momentum. What does that say about the force on the object? If I can have a constant momentum, how's my force? It's constant. Right? It's basically a force is equal to the rate of change. If I have a constant momentum, it's 0, but if I have a constant increase of momentum, I have a net force. What does that tell me about the acceleration of the object? If I have a net force, I have an acceleration. So this CubeSat continues to accelerate. It's not just a fixed speed, it gets faster and faster and faster as momentum is added to the system. Okay? Let's move on. This is the really fun one. There's 1 or 2 left. This next one, I'm going to ask a volunteer to do it because I'm too afraid. Okay. We'll come back. Let's put this up. I'll leave it up. So there's another kind of momentum that we're going to introduce, and you'll see it in problems. Okay? It's actually very simple. It's a simple quantity very similar to what we've been doing. Okay? So I can write down this thing called angular momentum. And it has a radius. I take the radius of some circle. Again, it's like momentum in a circle. I can think of a mass moving with some tangential velocity. So you see that if I look at this mass times velocity, that looks like momentum, right? Mass times velocity is momentum. So I can write down this thing called angular momentum that has radius times mass times tangential velocity. What is this? Is this circle rotating in the positive direction or the negative direction? Positive. So we will say that if my angular momentum is in a direction that's rotating this thing in a positive direction, it's a positive angular momentum. If it's making it rotate in the other direction, what is it? Negative angular momentum. So just like everything else, it depends on that rotational direction. So in uniform circular motion, going back to this old topic, the length or the angular momentum is a constant because r, m, and dt are all constant. This isn't in general true. This is a very specific case. And you can note that the linear momentum, so again, this kind of momentum of that object, is it constant? Is it constant if it's moving in a circle? Absolutely not, because there's an acceleration that is constantly under. There's a centrifugal force. Okay? So here's what we have to do. And this will get fun in a second, I promise. I have to think about this quantity, angular momentum. If I have a mass spinning around in a circle, I have an angular momentum. There's a radius, there's a mass, and it has a tangential speed. So it has an angular momentum. Anyone ever played with a fidget spinner? What's the stupidest kind of beginner level trick with a fidget spinner? Yeah, exactly. Right? And then, once you do it, what do? You balance it on your hand. Right? You say, oh look, I can hold it on my thumb and just spin it. And it has the ability to just kind of sit there. Did you ever take the fidget spinner, spin it really fast, and try to turn it? What do you feel? You feel a force. Okay? This is actually a torque. And we're not going to have too much time to talk about it, but that system basically wants to stay spinning in the same exact axis of rotation. Okay? So if I wanted to write that down for the fidget spinner, I would have to sum up all of the mass that makes up the fidget I would call its angular momentum the sum of all of those pieces of mass, their radii, their mass, and then the tangential speed. Does that look familiar? Right? We've done all of this kind of before. Remember, the tangential speed in rotational motion is just the radius times the angular speed. Test question from test 2. If I have a whole bunch of masses spinning around in a circle that are all connected, do they have different angular speeds or the same angular speeds? The same angular speed, right? So every object in this circle has the same angular speed. And so I can rewrite this as this quantity, the mass times the radius squared. What's this called? Where are my nerds? Mass times radius squared, when you add them all up, this is called the moment of inertia. And I multiply that times the angular speed. Okay? So angular momentum, let's write it down really simply. Here's how we write down angular momentum. Angular momentum is the moment of inertia times speed. Okay? Let me ask, if I have two big pieces of metal that I'm holding, oh, these are really good. Okay, not terrible for what I'm going to show you. If I held these two masses out here, I have a moment of inertia. When I pull them in close, did my moment of inertia get bigger or smaller? Smaller. Smaller, why? Because the radius shrunk, and it goes as radius squared. Okay? Can I have a volunteer? Are you sure? Yeah, come on down. Yeah, come on down. Okay.
This one.
You get sick?
No.
If you smoke.
Sit or stand?
Stand on first.
Oh shit, here we go.
Okay, wait, watch. Everybody, tell everybody your name.
Andrew.
What? You have a nickname. Okay, I'm going to turn you this way so you're facing that. So it's hold still.
Great pose.
That's like he's in a store window. Okay, stay right there.
Oh god.
Okay. Try to center yourself. So, like, if you turn your hips, does the wheel turn? Oh, pretty good. Okay, you look strong enough. Well, hook them on your finger. Yeah, now hold them out as far as you can. Okay. Now hold that for about a minute and a half. Let me find my laser point. Okay, there you go. Now, I'm going to spin him with an angular speed. He's not an idiot. I'm going to spin him with an angular speed. This is really scary.
You're telling me.
Okay, what happens if he pulls those in towards his chest? Do it.
Oh shit.
That wasn't fast enough. Let's do it again. Ready? Okay, pull him in.
Oh shit!
Okay. So what's going on? Okay, take a break. It'll slow down. There you go. Okay, so you can settle down. Wait, don't leave yet though. Okay. So what just happened? I had a system that was rotating. What was the force applied to the system? The force of me on his hand. Okay? Was that force applied at a radius from the center? Absolutely it was. I pushed his hand. Okay? Where's his center? Hold your arms out. Where's his center axis? Right out of the fontanelle of his brain. Okay, the fontanelle of the skull. His radius is at the hand. I applied a force. Let's do it again. Stand there without the weight. Stand there. Arms out. I applied a force right at his wrist, tangent to the circle. What is that called? No. A force applied at a radius perpendicular to the radial vector. We called it a torque. Oh no, everybody now. Okay, I'm going to make him undizzy by going the other way. When I apply this force, I'm applying a torque to this. I'm applying a torque on the system. What does that mean about the system? I'm adding a force. I'm increasing the momentum of the system. There was a fixed angular momentum. Now, come on down for a second. Let's stare at this equation. Shh, come back to me for a second. Let's say I gave him an angular momentum L, some value. And he was holding these masses out at the limits of his arms. Was his moment of inertia larger or smaller than it was when he pulled it in? Which is larger? Out. So for a fixed angular momentum, which I gave him by applying a torque, he had a large moment of inertia and therefore a small angular velocity. Okay? Now what happens as he pulls this thing in? What happens to his moment of inertia? It is smaller, and for L to stay the same, what has to happen? His angular speed increased. Okay? This is conservation of angular. Has anybody ever seen this in Olympic skating? What is it called? I forget what that thing's called. Triple toe loop is one of them. But the one where they spin, did you ever see how they do it? They tuck first they run into it with their arms and legs out, they swing their legs, they pull everything in, and they start spinning like crazy. They're basically lowering their moment of inertia to increase their speed. How do they slow it down? They just spread their arms back out. They put their arms and legs back. It's the same exact thing that you just did. I want to do one more, but I won't. Go ahead. Thank you. Give him a round of applause. We'll do it next time. So, coming back to this last topic, we've seen all this before. There's nothing really new, except now we have a new quantity that cares about this moment of inertia. In his case, it was a pretty simple moment of inertia. It was mass at some radius squared, blah, blah, blah. But all of this could be true for any object that I put into rotational motion. And so what we're left with is now an entire kind of suite of Newton's laws, including rotational and linear dynamics. Okay? This is everything, except for one piece, which I'm not sure if I got rid of. Let me put it back. But basically we had all of these equivalents. Remember, we had linear force. It gave an acceleration through Newton's law. That linear force also applied a change in momentum. Right? We did this all today. That the momentum N times V changed. It increased when I applied force. Then we had the rotational equivalents. We had torque, which you all forgot, but is a force applied at some radius from the center perpendicular to the radial vector. I applied a torque to Andrew's arm. Okay? Then I had an angular acceleration that caused rotation, and I gave it angular momentum. So when I have an angular speed, omega, with an object with inertia, or a moment of inertia, I can have an angular momentum. Now what we went over today, and it's the last thing that we'll remind ourselves of when solving problems, is that in all of these cases, both linear dynamics and rotational dynamics, if there are no external forces acting on the system, what do we say about the momentum? It's conserved, it's fixed. If it started at 0, it stays at 0. If it started at some value, it stays at that value. When I spun him, he had a fixed angular momentum that then he used to change his angular speed. Okay? Next week, we're in energy. We're getting rid of all of this. And we're not coming back. We'll see it on the final exam. I won't talk about it. I'll see you guys on Monday.
Sorry. Look, I just came back to campus. I was like trying to grab my bag. I just came back to campus last night and I'm already ready to go on for the
Yeah. No, I think everybody is. It's checkout time. The good thing about the summer is that nobody comes back to bother me about their grade once they leave. Summer is so amazing that they don't